All right. Well, we wanted to show you the work that we're doing on the fault detector. That's the derivative that's aimed at A2A. And the hardest problem that we have in this job right to date is actually generating a signal set that we can work from. And understand that you can't generate a wire that has 8,000 volts on it and has a couple of hundred amps going through it without expending energy. There's no way to do that, and so we have no facility to do that, nor do we have a facility to generate a three-phase signal. So one of the big disadvantages we're facing in this job is that unlike the Australian fault detector, where we could generate the entire signal set and then scale it so that the fault detector thought it was looking at the right levels, we cannot do that in the A2A case. And so we had to come up with another way to generate a large voltage that could be used that was in phase. So what we did is we actually came up with a way to fake an input that could be used, and it's a two-stage process. Maybe what we should first show you before we talk about that is what the solution actually looks like. Now this thing's on, so I'm not going to stick my finger in here. This brownish looking thing down here that looks like an insulator is actually a capacitive voltage indicator device that's available primarily from an Italian company called Isores. And what we found out along the way that this is one of Isores' standard models. It's basically a high voltage capacitor. It has a capacitance of about 7 or 8 picofarads. All I've done here is just take the thing and screw it to a junk piece of plastic box we had laying around, and it's being driven from the source. The rest of the solution is actually a very minor modification of the existing LVA board. The modification is to add a cable for the voltage inputs. Normally the voltage inputs come out together as 4 wires in a single cable where they're driven by a stiff voltage source. In this case, they're not. What we do is we actually replace that cable by 3 sets of coax, and you can probably see the coax coming in. We changed that to a 3-meter piece of coax, and the length is important. It turns out you're not allowed to cut the wire. They'll pass through the front panel of the device in the same place where the voltage connection normally was. On the current side, the current is accomplished normally. What we've got down here is a way to fake the current input. So here I have an older first-generation slimline sensor that's hanging on a 4-turn coil that has a precise current that's being pushed through it by a precision source. One of the other problems we have in this whole thing is there's only one precision source in the company, and this is it right here. So when we have to generate an accurate signal that we know, there's only really one way to do it, and this piece of equipment is it. So once it's in service, you've had it. Okay, so what are we doing here? On the one side, on the voltage input, this would be the connection that would normally be made in A2A. So this terminal here is at about 8,600 volts right now, and it's feeding the top of the voltage sensor just the way the A2A situation would be. In order for me to get a reference signal on it, I have a 10,000 to 1 voltage divider hanging down there that gets me a reference signal I can see. And we generate, with the rest of this apparatus, the current signal is precisely in phase with that reference voltage signal. Both of those two signals are progressing into the LVA. This is just a waveform display showing that the voltage signal that we're generating, which is kind of the one with the serrations on it, is precisely in phase with the current signal that we're generating. And both of those signals progress into the LVA. Now the tricky part about all this is that the sensor that's being used, the voltage sensor, is not a precision device. It does not have a precise specification. It is approximately 8 picofarads, and the value matters a lot. And so what we have to do is that the major step in getting this solution to work as a voltage sensor is being able to have the instrument figure out what the value of that thing is. Once it's connected to it, it has to determine what the value is. The way that's being accomplished is the same way that the RG-DAT works, and that is during the installation, the instrument has to be told, okay, you're connected to a certain phase, and that voltage right now is X. And we've created a training algorithm which allows the instrument to discover what the value is, and once that's done, it writes that value into a one-wire device that's actually attached to the current sensor down here. So there's a one-wire buried in here. That's where we store the data, and I'll actually run that algorithm for you and show you the thing working. So what we're going to do, it's really pretty simple. Right now there's about, actually let me figure out really quickly what the voltage is over there, because it's not a stable source, so we need to have a look. The instrument says there's 84 490 volts applied. That's actually off a little bit. I happen to know the correction factor in my head. Let's see. So there's 8626 on there. So we're going to train the unit. We're going to tell it there's 8,626 volts applied, and we're going to see what it does. So that's just a thing. John just finished this software this morning. It's a routine called FDCal. And essentially all you do is you tell it what the measured voltage is, 8626, and you train it, and it says okay. You write it in the one wire, and that's it. That's all the customer has to do in order to do the installation. So basically the installation is get the thing connected to the voltage sensor however you choose to do it. You're not allowed to cut the cable. The cable is as furnished. We are furnishing a small piece of safety equipment on the bottom of the sensor that keeps the voltages from getting too high. And if you think about it, what you'll find is that because that's just a capacitive device, if there's no load on it, the terminal that's at the bottom can raise to the line potential without, if it's not held down. So we are furnishing a little piece of safety equipment that holds it down to some reasonable voltage so you don't hurt yourself. But anyway, they got to get the end of the solution connected to the voltage sensor on the bottom. And once they do that and put the current sensor around the appropriate same phase, they run this little routine called FDCal, and away you go. So let's just quick see if it's getting about the right answer. I just caled it to 8626. Let's see what it's reading. 8616. Not too bad. That's this value right here. You can hardly see it. Focus is terrible. Well, you're going to have to take my word for it. It says 8616 on there. So that's where we're at. With this accomplished, that's about it for the software development. All the rest of the fault detector software is identical. It all works. It's all been established, all been tested as thoroughly as we know, and it's been running out in South Australia Power Networks for probably almost 6 months now. So without a single hiccup, it's run very, very well. So once this ability to couple the voltage in is done, and we do a little tidy up, we're done, and then becomes the problem of passing it over to Lee to get the DMP3 interface written onto OpenGrid. That probably will be the largest challenge of this job, I think, at this point, because we're I think in pretty good shape. Hope that answered the questions and shows you what we're doing. And let me just make a point that we are severely disadvantaged in this job for a couple of reasons. One, we don't have a three-phase source that could generate 3 phases of voltage and 3 phases of current. We only have one, and it's unregulated. So this is slowing us down. We're definitely limited by equipment. This is the first time, frankly, that we've been this limited by equipment. We managed to get through the Australian development by kind of hook and crook and other stuff, and it was okay. But we are severely limited by lack of facilities right now, and that is hurting us. But we'll get through somehow or another. That's it. Any questions, send me a note. We'll do the best to answer.
Thank you, sir.
Bye.